In Nottingham we have a big research group and we do lots of work on electrical systems and transportation. I don't want to speak too much about that, but we have about 140 people at Nottingham doing research work in the electrical engineering area, power electronics and electrical machine drives. So a big team of research. So the things you're going to hear about in the next 20 minutes, it's not just my research, it's the research of a big group of people. I put this slide in just to show that we have lots of links with Chile. So these are the universities that my research group has active links with. And you'll notice there's lots of lines going to Chile down here. So we have a long history going back to the, I think it says there, to the late 1980s of working with universities in Chile. We have a number of papers that we've published, lots of citations, various awards and so for the work. Working in wind energy systems, solar energy systems, microgrids and the future networks, and large motor drive systems. So I think you'll recognise most of those areas. What I want to talk about today is the growing trend we have for electrification in transportation. I noticed the last speaker mentioned this. I suspect I might be disagreeing with him on one or two points. So what I want to do is to have a look at some examples of transportation electrification, look at the challenges, look at what we as engineers have to solve. Our job is to solve problems. And I'm going to do that using some examples of cars, motorbikes, planes, and maybe ships, to have a look at how these things differ. Anybody who tells you that an electric car is a new idea is lying. Does anybody know when the first electric car was designed? The answer is not 1902. No? Nobody want to guess? It's nearly 100 years before that. It was back in 1828. So if you think we're working on new ideas in electric transportation, you're wrong. The first cars were electric. What went wrong? Well, they had a very low range and they were very expensive. Does that sound familiar? They don't go very far and they cost too much money. Exactly the same as today. Oh dear. Right, so by 100 years after the first electric car had been produced, I've chosen the Hungarian, but there's others around that time. All production had ended due to cost and range, because the electric car cost $200 US and the petrol car in those days cost $600 US. Has it changed? Well, no, they're still expensive. I've chosen these two examples just to illustrate something. Now this is where I need your participation. Two cars, Nissan Leaf and the Tesla S. Okay, so the Tesla S is a big sports car and the Nissan Leaf is a very small city car. Who in here would, if they had the money, who would buy the Tesla? God. Who would buy the Nissan Leaf? Oh, not many. Right. It's important. Well, it depends where you are in the world. I asked that question in China, and everybody goes for the Nissan Leaf. I asked that question in North America, and everyone goes for the Tesla. Okay? It's important in many parts of the world, particularly in the Americas and in Europe, that cars are exciting, that cars are big, and that cars have the range. And if people have the money, they will buy them. I think this car was a disaster for electric vehicles. It's slow, it's small, it's not very exciting. I think this is the car that will help electric cars happen, because it's exciting. We'll come back to that in a moment. So, the advantages of electric cars are the low running costs, lots of incentives around low tax, free parking at my university. If you drive to my university, you get free electricity to charge your car. Comes from solar panels. And lots of incentives there to try and make things greener. With a social conscience, it also reduces pollution. Great. The disadvantages, range anxiety. We're worried that we're not going to get to the end of our journey or to the next charging point. That's not a real concern if we manage it correctly, but it is a concern people have. And the high purchase cost because of the battery technology. Electric cars use exactly the same battery technology as my mobile phone. It's lithium-based technology. Good for your economy because you mine lithium in the north of Chile, but it's expensive. So is range really a problem? Well, if we go back here, this Tesla will do over 400 kilometres on a charge. Yeah, that's 3.5 hours of driving on Route 5. I want a cup of coffee at the end of that. Yeah, it's important that we remember that this is quite a distance, and that if I can charge that car in 20 or 30 minutes, it's not a problem. I can drive very long distances, as long as the area I'm driving in has the infrastructure, the electrical energy infrastructure to support that charging. And that's important. What do we need to make electric cars better? Well, at the moment we're up here with lithium-based technologies. 100 years ago they were down here with lead-acid technologies. There's a trend line. What we need is the next battery technology up here. Something which has a better volumetric and energy density. If I knew what that technology was, I would be very rich. If you know what that technology is, I suggest you develop it quickly. We need to have lighter batteries with more energy storage. If we have that, the range goes up, the cost of the cars comes down, and we will all be driving cars without fossil fuels. In the meantime, some things are going to have to use hybrid technologies. And these slides just very quickly try to develop a language around what we mean by hybrid and all electric. So the first one I have here is series hybrid, where I have a petrol engine driving a generator, some power electronics. I'm a professor of power electronics, so that's good news. Followed by an electric motor driving the wheels. Is this a new idea? No. They've been doing this in railway traction for nearly 100 years, ever since the steam trains were replaced with diesel electric trains. So this is a very old system. Adding a battery is a slightly newer one. Okay, so a nice old idea, it works. And that is good for driving in cities. Lots of stop-start driving. If you take a Toyota Prius, well, we'll come to Toyota Prius in a moment. If you have a look at the parallel system, you have the petrol engine, a motor generator driving the wheels, but we can also put energy in or take energy out using the power converter connected to this motor. So that's a parallel hybrid. The electrical energy is in parallel to the petrol engine, and that's good if you want to do lots of long distance driving, lots of driving at speed over a great distance. You find this is more efficient. If you want to go all electric, all you do is you delete that petrol or diesel engine and you substitute some energy storage, usually a battery, could be a fuel cell, to a power converter, to a motor to drive your wheels. Very basic electrical propulsion system. It doesn't matter if it's a car, a motorbike, an aeroplane, or an electric ship, as we'll see. So, talking of aeroplanes. Can we fly? Actually, I should say, this is Airbus, the first Airbus two-seater aircraft. It flies for about 20 minutes on a full charge of the batteries, and each of these motors driving these fans is about 30 kilowatts. So a very small little aircraft, but it just shows that we can actually fly with a battery-powered aircraft. If we want to be a little bit more realistic, we can start looking at the hybrid technologies. This is one, it's a concept at the moment, where we have a gas turbine here at the front. So we have a conventional engine driving one propeller, but it also drives a generator, and that generator drives motors that power the two propellers on the wings. So it's a hybrid system. I've still got one conventional engine, but I have two electric motors. It reduces the drag of the aircraft, so the extra weight is paid for in the drag reduction, so I still use less fuel. Okay, and then we can start doing the things that power electronics engineers like to do. We can look at different circuit topologies, different electrical machines, ways of mounting the power electronics, losses, and all the good things we do as power electronics engineers to feed into the system design. Here's another system that's being considered for larger aircraft when you're looking at having gas turbines on each wing, but then lots of electric propulsion to get more distributed propulsion along the wing. By doing that, you can get certain aerodynamic advantages for your aircraft, hopefully using a little bit less fuel. As we go further ahead, you might end up with the gas turbine driving a generator actually inside the aircraft, and then on the wings you might just have electric motors driving the propellers to actually make the aircraft move through the air. Lots of different system choices, a lot of time. Why would you do this one? Well, putting a big engine out on the wings creates drag. Moving that engine inboard in line with the passengers reduces the drag of the aircraft, so you use less fuel. It's all about the fuel. That's the expensive part when you fly on an aircraft. To do that, we've got various roadmaps. This is for electrical motors, looking at how over the next 20 years we might be able to reduce the size and the weight of electrical motors to make all this possible. If we can't follow this roadmap, these ideas fail. Very simple. Challenges for electrical engineers. I'm not going to bother that one. So to feed the energy for all this, we need to consider how we organise our generation. I know we've seen some of this already today, and how we have smarter grids with more distributed generation. So at the top there is something that looks like a conventional electrical system with some big generation feeding through some transmission lines, distribution lines, down to the consumers. If we want to make this grid smarter, if we want to introduce more PV plants, more wind farms into that network, so we have more renewable energy, what we find is this traditional unidirectional flow of energy fails, and we have a bidirectional flow of energy. If I have PV plants connected at the distribution level, energy might flow back from the user end. To enable all that to happen and the grid to remain stable, you need to have some communications. You need to know what is happening within the grid, and this is the whole concept of the smart grid, is to put on top of the bidirectional flow of electrical energy a bidirectional communication system. So this is not just the energy company telling you the price of electricity next year. This is a real-time system where the energy company can find out how much energy you're using every minute, and you can find out what's happening on the network. So maybe the appliances in your house can behave differently depending on the network conditions. So if demand is very high, maybe you have to wait for your washing your dishes or washing your clothes. Your washing machine might wait until the energy is cheaper. Why not? So have lots of different communication links to make all that happen. So I said I'd come back to something exciting, so I started talking about cars. I want to sort of just bring things together a little bit, looking at motorbikes. This is the University of Nottingham's race bike. To give you some idea, this will go around a racetrack at speeds of up to 300 kilometres an hour. This is not me, and this is not me. This is a professional rider. This is faster than a superbike around a Formula 1 circuit. Okay, so this is a piece of proper racing machinery, and it's all electric. Okay, it has a supply of about 20 to 25 kilowatt hours, depending how we configure it. We've had power levels up to nearly 200 kilowatts at the back wheel. To give you some idea, this will accelerate faster than the Tesla sports car, but we only have one small rear wheel rather than the two big wheels of a Tesla. And it weighs, depending how we configure it, about 250 kilograms. So it's a big, heavy, fast bike. You need to have a lot of skill to go around corners at 200 kilometers an hour on that bike. I haven't got that skill. Why do we do it? Well, I want to promote electrical vehicle technology. I want it to be exciting. I want my students to go into the industry and to solve the problems that need to be solved. I want to push the boundaries of technology. When a company makes a car, so when Nissan made the Nissan Leaf, it had to work, it had to be safe, it had to be a technology that they could sell. When I'm racing a motorbike, it's dangerous. The accidents happen. So I can take risks with the technology. It doesn't matter if I don't finish every race. So I can really push the boundaries. I can test new technologies. If something goes wrong, well, we'll fix it. Okay? So we can try new devices. We can try new motor designs. I have PhD students whose whole PhD is optimizing and building a motor to go on that motorbike. And we can test new ideas, and we can look at that. One of the ideas is transportation of lithium-ion batteries by air. How do we make it safe to transport batteries? At the moment, the rules are somewhat prohibitive. It makes it very difficult for us to race internationally. But that also makes it difficult to fly cars around the world. But we can also test new battery technologies, and we can look at the application of autonomy. How do we put autonomy into a race vehicle and race those cars? Not actually that exciting for the human being, but very exciting in terms of testing that technology and actually making sure that technology will work in very extreme environments, but also a slightly safer environment for the general public. So lots of reasons why we might do that. The other reason we like doing this is because we win races. We've been the European champions for 2 years in a row. We've been third at the Isle of Man TT for 2 years as well. The only team that beat us is Honda, and their budget is about 100 times bigger than mine. So hopefully there's my team looking quite happy. If you don't know what the Isle of Man is, it's back to geography. It's a small island here in the Irish Sea, and the racetrack on that island, they close the roads and you drive around the island. It's about 60 kilometres. It's the most dangerous racetrack in the world because there are no runoff areas. It's big walls and hedges and fences at the side of the track. It's a very dangerous place to race. Great fun. So, in conclusion, hopefully in my time, cars and autonomy. We need to have good standards for using this technology. We need to have good infrastructure if you want people to drive electric cars. For example, in Chile, I can see how all the service stations on Route 5 could have rapid charging points. Why not? then people will drive the length of the country in electric cars. Electric trucks I've not talked about, but to me that's a good early area for autonomous vehicles. We have trucks driving up and down most of the countries in the world. If you make them autonomous and remove the driver, you make better use of that expensive facility in the truck. Motorbikes, it's an exciting way of pushing the boundaries of speed and technology. But what all these things are relying on are the new technologies coming through. So if you look over here at the impact of new technologies against the technology readiness level, you'll see superconducting machines here, very low technology readiness level, still at the university research stage. But you'll see new magnetic materials and power semiconductors using silicon carbide and gallium nitride are here as high impact, and these are technologies that are beginning to happen today. And in between you'll find things like additive manufacturing, this is 3D printing, and new thermal materials, things that will have a big impact on electrical systems in the future, maybe not quite ready yet. Okay, so thank you very much for listening. I hope you found that interesting. Thank you.